So, we'll be starting with a new topic, that is magnetic effect of current. So, we'll be discussing about magnetic effect of current. So, Oersted was the first scientist who told that if current is passing through a conductor or a wire, then a magnetic field is created around it. So, basically, the other name of this topic is also called moving charges and magnetism. We have studied in previous chapters like electrostatic, when a charge is at rest. Study of charge at rest is called electrostatic. Static means rest, and when there is a charge, you can find a spherical space around this charge representing a field where you can calculate potential due to that charge, where if any other charge will be brought, it will experience a force due to the presence of the earlier charge. So we have discussed all these things in electrostatic. You go and check my other YouTube videos for understanding. But here, what we are saying, if a charge is moving through a circuit, or charge is moving means a current is flowing, because basically I is equal to Q by T. Flow of charge with respect to time or rate of flow of charge is called current. So when a current is moving or charge is moving in a conductor or in a wire, a magnetic field will be created. This idea was given by Oersted. Then Biot Savart came into picture, who suggested that how to count how to count the magnetic field produced, or how to quantify. Actually, Oersted gave qualitative idea about magnetic field, but Biot Savart gave a quantitative idea about magnetic field. So let's say this is where we are considering a small current is moving I, and small length element is dl. Length element dl vector. Remember, current is a scalar quantity. Current is a scalar quantity, but length is a vector quantity. Okay, so when a current is passing through this conductor, then a magnetic field will be created around it. And if you raise your thumb along the direction of this, raise your thumb like this, just raise your thumb like this, it will give the direction of current, and curl all your fingers along the direction of motion. Curl all your fingers like this. So here I'll get a magnetic field which is towards the paper. Let's say the magnetic field is dB. Magnetic field is also a vector quantity. It is directed towards the paper. So this sign, and here it is outwards, means towards you. So outwards is represented by a dot point. And let's say this distance is r. And let's say this ideal is making an angle theta. So if I draw a simple thing, and this is r, this is theta, and this is ideal. So ideal and r vector, r is also vector quantity, radius vector, are making an angle theta with each other. And we want to find out magnetic field here. Let's say this point is P, and magnetic field here is towards the paper. This point is P, where I want to find out magnetic field due to ideal current using Biot-Savart law. And here dB vector is towards the paper. So I'll discuss about Biot-Savart law. So let me erase this. So according to Biot-Savart, the small amount of magnetic field generated at a point due to a length element dl is dB. So this this dB is directly proportional to dl. dB is directly proportional to I. dB is directly proportional to sine theta, but dB is proportional to inversely proportional to r square. So if I draw a diagram, then this is the story. Here I am taking ideal. This is theta, this is r, and I am finding here dB. Already I have mentioned. So already I mentioned this. Let me erase out for clear understanding so that I can repeat again. So already I have seen that here I'm getting dB due to ideal current flowing through this region, and this is theta and this is r. So my Biot-Savart law will be dB is proportional to I, dB is proportional to dl, dB is proportional to sine theta, and dB is proportional to inversely proportional to r square. So dB is proportional to I dl sine theta by r square. So dB is equal to mu naught by 4 pi I dl sine theta by r square. Sine theta by r square. So Biot-Savart law suggests us dB is proportional to ideal sine theta. So dB equal to mu naught by 4 pi I dl sine theta by r square. This is actually Biot-Savart law in scalar form. Now I'll be writing Biot-Savart law in vector form. So this is the point where I want to find out dB. This is towards the paper. Now this is my ideal. This is theta. This is r vector. So if you apply cross product and if you are moving from ideal cross r, then magnetic field is towards the paper. So I'm writing dB is equal to mu naught by 4 pi ideal sine theta by r square. If I'm trying to write it in vector form, now dB vector will be mu naught by 4 pi. Now sine theta is angle between ideal vector and r vector. So I can write ideal vector cross r cap by r square. I cannot write r vector here because it will change the whole magnitude. So ideal magnitude is ideal, r cap magnitude is 1. So ideal cross r cap will be ideal sine theta into 1. So it will be ideal sine theta r square. But if I want to write out in a complete vector form, then I can change that like this. That is dB vector equal to mu naught by 4 pi ideal cross this r cap can be represented as r vector divided by r square is there before, r vector divided by r or magnitude of r. So now dp vector will become mu naught by 4 pi I dl cross r vector by r cube, or sometimes this r cube also written as r vector magnitude cube. So this is Biot-Savart law in vector form. This is Biot-Savart's law in vector form. I hope all of you are getting clear about this. We'll discuss some problem in the next class. Thank you for attending the video. Please watch, like, share, and subscribe.